Hello, this is our ME 380 final presentation about non-traditional machining. We're group 8 and we are going to talk about chemical machining. So, first we want to talk a little bit more about non-traditional machining and what it means. So, non-traditional machining refers to a group of processes that remove material using forms of energy other than direct mechanical cutting. Unlike traditional methods that rely on hard cutting tools and high forces, non-traditional machining use electrical, thermal, chemical, or high-speed mechanical energy to shape materials. So, like I mentioned before, there are four different types. There's mechanical, thermal, electrical, and chemical. And these are some of the types of these sections. So there's ultrasonic machining or what water jet machining for mechanical. There's laser beam machining or electron beam machining for thermal, electrical discharge machining or wire electrical discharge machining for electrical. And then for chemical machining, there's chemical machining and electrochemical machining.
So I'm going to talk about history. So chemical machining dates back around 2300 BC in ancient Egypt, where craftsmen used natural acid like lactic acid to etch copper for decoration. This was one of the early ways people used chemistry to shape material without tools. During the Renaissance, the process became more advanced and was often used to decorate armor. Metalworkers would cover certain areas with prototype coating and use acid to etch detailed patterns into the exposed parts. This period marked a big step forward in using chemistry for designing and surface work.
So, chemical machining. So defining chemical machining, it's a non-traditional machining process that removes material through controlled chemical reactions. Instead of cutting with a tool, chemical machining uses acid or alkaline etchants to dissolve specific areas of a metal surface. The process is contactless, meaning there's no heat or mechanical force involved. A maskant is a chemical resistant coating that acts as a protective barrier to the areas that shouldn't be etched. The areas that are exposed chemically dissolve the material to create cavities or patterns.
Types of chemical machining. Number one, chemical milling, a process that removes surface material through chemical etching to reduce weight and form precise shapes. Commonly used in aerospace and automotive industries to produce strong, lightweight parts with contours and pockets. Number two, chemical blanking, used to remove material from specific areas of thin metal sheets, creating intricate shapes and patterns. Ideal for electronics and micromechanical components like circuit boards due to its precision with complex designs. Number three, gaseous chemical machining, a specialized method that uses reactive gases to remove material, particularly effective for deburring and reaching areas inaccessible to liquid etchants, perfect for intricate, delicate components. Number four, chemical engraving, creates fine designs and patterns on thin metal surfaces by selectively removing material, similar to chemical milling but used for smaller, more detailed work. Number five, photochemical machining, an advanced technique involving photoresist and UV light exposure to etch precise microscale features. Produces stress-free, crack-free components used in microelectronics, circuit boards, and fine meshes.
Okay, so process types in chemical machining. So there's cleaning, masking, scribbing or imaging, etching, demasking, and inspection. Cleaning just basically means removing dirt, grease, and oxidation from the metal surface. Masking is applying a chemical resistant maskant to protect the areas not to be etched. Um, Scribbing or imaging, defining the pattern by cutting or exposing the maskant in desired areas. etching, expose the part to a chemical etchant to dissolve the unprotected metal. Demasking is removing the remaining maskand to reveal the finished part. And then inspection would be to just check the dimensions, quality, and the surface finish of the final product.
Common etch in materials. The materials are aluminum, copper, stainless steel, polymer, polyamide, ceramics, aluminum, silicon, and carbide. Common chemicals, acids such as nitric acid and sulfur acid, alkalis, sodium hydroxide, and potassium hydroxide. Etches, ammonium persulfate, in safe environment, use PP in proper ventilation, recycle neutralized chemicals to reduce environmental impact, mass materials, photoresist in polymer films, and material mass protects area from etching. Chemical milling in detail. Chemical milling is the process of using chemical in a controlled way to remove material from workpiece. Process: clean the surface before anything else. The part that's going to be machined is cleaned really well to get rid of any dirt, oil, or any stuff that might mess the etching. Applying the mask. Next, a special mask or resist is put in the area that shouldn't be attached. This layer protects those sections from chemical solution and is usually made from materials like plastic coating or films that can handle the chemical used. Etching process. Once meshed, the part is exposed to chemical solution. This could be either acid or basic that eats away at the unprotected metal. These steps remove the material only for the area that aren't covered by the mask. Removing the mesh. After etching is done, the mesh is peeled off, revealing the final shape or design in the part. Final touches. Depending on what the part is for, it may go through some extra steps like another cleaning, protective coating, or surface treatment to get it ready for use.
Advantages of chemical machining. Chemical machining eliminates the application of mechanical forces on thermal stresses on the workpiece. It's also well suited for machining thin, delicate, or heat sensitive components. It's also capable of producing highly complex and intricate shapes with fine detail, results in burr-free surfaces with good surface quality, involves relatively low tooling and setup cost, particularly beneficial for low volume production, effective for materials that are difficult to machine using traditional methods, really smooth finish, and tight tolerances, which is great for precision work.
Disadvantages of chemical machining. Chemical machining presents several disadvantages, including slow process due to low material removal rate, making it ideal for precision rather than speed. Material restrictions. Only compatible with select metals, ensuring high-quality results for specific applications. Chemical handling involves hazardous substances requiring strict safety protocols for controlled environments. Process sensitivity. Final quality depends on the etchant used and the precision of the masking process. Environmental impact. Uses chemicals necessitated proper waste management and disposal systems. Result, variability, risk of inconsistencies from chemical buildup and contamination, highlighting the need for clean room standards. Applications of chemical machining. High precision needs. ideal for applications requiring tight tolerances and metal removal within just a few microns. Complex shapes, used for selective removal material from formed or irregular shaped components like forging, casting, or extrusions. Burr-free detailing, perfect for producing intricate burr-free stampings with clear edges. How industries use chemical machining. Aerospace for lightweight, high-precision components. Electronics for circuit boards, microelectronic parts. Medical for surgical tools and implants. And automotive for lightweight, detailed parts for performance.
Mathematical considerations in CHM. So some formulas used in this method is etching rate, which E rate is the rate of etching that is the depth of cut, the T equals the immersive time, and the material removal rate, which is the MRR, or the E, which means electrochemical equivalent of the material. I is for current, F is for the Faraday constant, which is approximately 96,485 coulombs per mole, and density of the material.
Process parameters. Unlike traditional methods that use mechanical force or heat, chemical machining relies on controlled chemical reactions, making it sensitive to many factors that can influence etch rate, precision, and surface quality. Some of the key process parameters are etchant composition, which determines the reaction rate, and it is dependent on the material compatibility. Etching time controls the depth and resolution. If etching time is too long, then undercutting can occur. Temperature. Higher temperatures can increase etch time, but may reduce accuracy. Masking quality. Mass adhesives and patterning resolutions are crucial for accuracy. And material. The type of material used along with its thickness affects how fast and evenly the material will etch. Proper parameter control is essential for uniform material removal, minimal undercutting, and high dimensional accuracy.
Environmental and safety concerns. Environmental concerns. 1. Chemical waste disposal. If not properly disposed, hazardous waste generated from the process may contaminate soil and water. 2. Air pollution. Volatile organic compounds and fumes released during the process can contribute to air pollution and damage the ozone layer. 3. Resources. Strain on natural resources can occur due to the use of large quantities of water and chemicals. Safety concerns. 1. Worker exposure. Direct contact with chemicals can be physically dangerous and may cause injury or illness. 2. Fire and explosion risk. Many chemicals used during the machining process are flammable or reactive. 3. Equipment hazards. Improper use of machinery or chemicals can cause accidents. Comparison with other non-traditional methods. 1. Material removal process. In chemical machining, we utilize chemical solutions to dissolve material selectively, which is important when dealing with complex designs and materials. On the other hand, other methods rely on physical processes such as electrical discharges, laser beams, or ultrasonic vibrations in order to remove material. 2. Stress on workpiece. In chemical machining, no mechanical stress is occurred, which preserves materials that are delicate to work with, while in other non-traditional methods, may cause mechanical stress due to abrasive particles. 3. Environmental impact. In chemical machining, it usually generates hazardous chemical waste that needs to be properly disposed of, while in other methods, uh, they usually consume high energy and generate dust, which poses different threats to the environment.
Industrial examples. Number 1. Aerospace. Chemical milling is utilized for its ability to reduce the weight of an aircraft while maintaining structural integrity. The process ensures high precision without introducing mechanical stress. Number 2. Medical. Chemical machining is beneficial to this industry due to its ability to produce surgical instruments with complex designs. Etched metal components with clean and sharp edges are essential for implants and diagnostic devices. Electronics utilized to manufacture printed circuit boards with intricate patterns. The chemical etching process makes it possible to create fine details that are essential to modern electronics.
Future trends in chemical machining. Future trends can be found in sustainable etchants, hybrid processes, nano etching, and automation and AI. For sustainable etchants, new environmentally friendly chemicals to reduce toxicity. For hybrid processes, combining chemical machining with laser or plasma machining for better efficiency. Nano etching, applying chemical machining to nanoelectronics and micro-electromechanical systems. Automation and AI, AI-driven process control for consistent quality and speed. Thank you for watching.